All right, welcome back, everybody. And now we are jumping into investigation 3, which has a lot to do with radiation. And we're going to talk about some of the major applications of this radiation in meteorology. And the first application we're going to talk about is through the use of weather satellites. And weather satellites are very important because they allow us to identify, track, and forecast storm systems. Before what was called the satellite era, which started in the 1960s, the only way that we could determine the location of a storm system would be through actual observations. And that's good over land, but when you're over the ocean and there's a giant hurricane out there and there's no ships or no buoys or anything that can locate it, that could be a problem. And so satellite images are very, very important because they help us to identify where storms are. And this is an image that I took a couple days ago of a storm system that was impacting California and producing a tremendous amount of rain. And the satellite image basically allows us to view the structure, the evolution, and the movement of the storm. And the storm system, as you can see, features a pretty well-pronounced swirl of clouds, and then this long line of clouds here, which is associated with a frontal system. But let's actually talk about how this works and what type of satellites there are and how this applies to meteorology. And then the hope is that this will help prepare you for Lab 3A. All right, so first off, the way that satellites work is obviously they're in space, and there's actually different types of satellites for different applications. One of the types of satellites is what's called a polar orbiting satellite. And basically what these satellites do is they orbit the entire world in what's called a polar orbit. And the idea behind a polar orbit is they start at the North Pole, then they travel all the way to the South Pole, then back up to the North Pole, then back down to the South Pole. Meanwhile, as they're orbiting, the Earth itself is rotating. And so after every rotation, they get a new view of the Earth. These are very helpful when collecting certain data sets, and there's some very important satellites out there that are really crucial in the field of climate science. For example, there is a satellite called Terra that has some really important instruments on it, such as the MODIS instrument, which is a very important radiation measurement instrument that rotates around the world. But these type of satellites also have one major drawback. So the positive is that they end up giving you a data set for the entire world at the exact same local time every day. So that's a major positive, but the major negative about them is that they're never present over the same location over a full daytime or over a whole period of time. Well, thankfully we have a second type of satellite that can actually help us with that, and it's what's called a geostationary satellite. So the way this satellite works is instead of orbiting in a polar path, it orbits in a path that is much more parallel with the equator. And the geostationary satellites actually orbit at the same speed that the Earth is rotating in. And the benefit of that is that the satellite is over the same location constantly. Whereas with polar satellites, the satellite is constantly leaving the direction where it's over and moving to a new direction. In the case of geostationary satellites, the satellite remains stationary over the same location during the entire 24-hour period. So it's planted over that same location. It's looking down at that same location constantly. And today we're going to talk about geostationary satellites. Now with that said, you have a geostationary satellite and it's looking down on the Earth. And it's looking for a bunch of different things, and there's actually a bunch of different things it can measure. One of the most important things is clouds. Going back to this image right here, the location of clouds help us identify the location of storm systems. And so we want to be able to identify where are clouds, how thick are they, how organized are they, because that then indicates a cyclonic system or some kind of organized weather system. And then what kind of precipitation do they have with them? So going back to this image, there's actually two ways that satellites do this. The first way is what's called a visible satellite image. Imagine if you were on the International Space Station and you were looking down towards the Earth and you see all the individual clouds and you see everything. Well, essentially that's what a visible satellite image is. It basically is just looking down and essentially getting a snapshot of the ground beneath it. Now, the way that it does this is it uses reflected solar radiation off of the clouds. So basically what happens is sunlight hits the cloud. So if you have a cloud here, I'll draw one. Okay. And let me pick a good color here. I'll pick a blue color. So let's say we have a cloud like this, very poorly drawn, but and then let's say we have some incoming sunlight. Let's see here. Let me undo that. Erased everything. Sorry about that. All right, so here's our cloud. So here's our cloud. And then here is our incoming sunlight. It hits the cloud, bounces back off the cloud, and then a satellite sensor, and let me draw one of those, a little satellite sensor, then appears and actually absorbs that radiation and measures that radiation. And then using that radiation, it can then say, okay, well, there's a lot of sunlight over at this moment, so this was likely a cloud, and very little sunlight reflected at this moment. Okay, that is land, and so on. And these visible satellite images actually have some pretty good positives to them. The biggest positive is that they are very detailed. Using a visible satellite image, you can actually see a ton of very cool details about storm systems, such as the eye of a hurricane. Visible satellite images actually really allow you to see the structure of a hurricane, to see the way that the eye is changing. Is it falling apart? Is it getting tighter? Is it getting larger? And that's just one thing, but they're very detailed. However, there are two main downfalls to visible satellites. The first one is visible satellites rely on reflected solar radiation. So that means that you need sunlight to hit a cloud and bounce off the cloud. This is only useful during the daytime. These satellites are essentially useless at night. They're essentially useless at night because there's no sunlight. And the other major downfall with these is that they rely on the amount of solar radiation reflected off an object to identify where clouds are. And there are some objects on the surface of the Earth, mainly ice and snow, that are just as reflective as clouds. And so oftentimes a visible satellite image can confuse snow or ice for a cloud. And so as meteorologists, we need to be able to discern the difference between snow and the difference between a cloud. And so it can get a little dicey there. Now, with that said, there are actually some technologies that make life a little bit easier when we don't have sunlight or when there's a lot of snow and the satellite image is confused. And these come in the form of what's called an infrared satellite. Now here's how this satellite works. Let me erase all of this. Whoops. Let me erase all the ink. Okay, and let me pull up, wrong thing. Here we go. Sorry about that. Okay, so the other type of satellite image is what's called an infrared satellite image. Here's how this works. If you've ever taken my Met 10 class, or I would assume somebody else's Met 10 class, you've probably been introduced to some of the major concepts of radiation. If you haven't, let me just take a moment and just tell you a few important concepts. The first concept that you need to know is that all objects emit radiation. And in my lecture classes, I always love to do kind of an Oprah joke where I tell people that, hey, you're all emitting radiation. And it's true. We're all emitting radiation. But the type of radiation and the amount of radiation that we emit depends heavily on our temperature. And what's actually cool is that you can use a sensor, and you can even get one of these from Amazon for like $10. And using that sensor, you can actually measure the radiation an object is giving off and determine its temperature. Well, infrared satellites do the same thing. And what they do is, as they're flying over a cloud, so let me draw a little satellite here. Whoops, there we go. So here's a satellite here. Rather than relying on reflected sunlight, the way that these work is they instead rely on the infrared radiation that clouds give off. And clouds are typically colder than the ground below them. And the main reason why is because they're higher in elevation. They have a lot of condensed water, oftentimes a lot of ice, and so on. But another really useful fact about clouds is that the taller the cloud, the colder the cloud top. And so what an infrared satellite can actually do is, as it's flying over a cloud, it can use that cloud top temperature, how hot or cold it is, to say, okay, this is a high cloud, this is a low cloud, this is a really thick cloud, this is a really thin cloud. And that can actually give us a lot of information about, is there a cloud there? How high it is? How thick it is? And that can tell us a lot about what's going on inside the cloud. Now, there are a few strengths to this. So the first one is, because this doesn't rely on solar radiation, this is useful 24 hours a day. And so this actually allows us to view clouds at night using satellite technology. It's also a lot easier to distinguish clouds from snow. Typically, snow is a lot warmer, per se, than a cloud top. And the only weakness really is that it's not as detailed as visible satellites. And typically, meteorologists use a combination of these two, visible satellites and infrared satellites. So here's how a visible satellite image looks. This is actually taken a day after the visible satellite image I showed earlier. And just looking at it, you can identify some pretty major cloud locations. So let me pull up my laser pointer. Here we go. And as you can see, there's areas of relatively bright white, such as up here, such as down here, and over here. These represent pretty organized cloud systems. Meanwhile, where you see a lot of dark, such as down here and over here, these represent cloud-free areas. These represent areas with clear skies. And so this is pretty useful to us. This actually allows us to distinguish clouds from clear skies. Now, the negative of this is that a lot of regions, as I mentioned earlier, are usually pretty snow-covered. Over here's the Rocky Mountains, and there's a storm system just to the west of the Rocky Mountains, but much of this right here over the Rocky Mountains is actually snow cover. And so it's really hard to distinguish a storm system from snow cover. And then again, the other thing that I mentioned is that this is actually only useful during the daytime, and I'll actually show an image sort of proving that in a moment. All right, here is infrared satellite. Now, if you notice, infrared satellite uses a lot of color coding. These are actually what are called enhanced infrared satellites, and they rely on the cloud top temperature. And here's how they work. You see a lot of areas of kind of this milky grayish. These represent relatively warm cloud tops, and typically these are very low clouds, lots of fog, and very, very thin clouds. And so lots of this milky gray down here and then up here. These again represent low clouds. On the other hand, if you notice, there are these blues. These represent cooler clouds, so they're a little bit thicker and they're a little bit taller. And then the taller they get, the colder their cloud top gets. And so the colors then shift from blue to yellow and then sometimes orange and even red. And very, very tall clouds may even have red with them. Now, one of the reasons why we even care about how tall the cloud is typically the taller the cloud, the stronger the storm. Very tall clouds are clouds that are fed by what's called convection, and that allows them to have a lot of energy to them and a lot of stormy weather to them. All right, now moving on, there's a few things I wanted to talk about that are asked about in this lab, and so I just wanted to help you with that. So the first thing that's talked about a lot in this lab is what's called the subsolar point or subsatellite point. And the way this works is that you have a satellite and it's floating over a location and it's stationary over that location. And the subsatellite point simply is the point on Earth that is directly beneath the satellite. So for example, right here, if you take a look at these two images, the satellite is located right at this red star. And then the location of the Earth, or the location on Earth, directly beneath the satellite, is the subsatellite point. One of the questions that they ask is the concept of where sunlight is coming from, and also what time of day is the subsatellite point located at. So here's a few things you need to know. Imagine the Earth, and imagine that it's rotating like this. So basically this location, this subsatellite point, is actually moving further east. And these globes, this actually is just like any map that I've talked about. North is on the top, south is on the bottom, west is on the left, east is on the right. And this subsatellite point, as the Earth is rotating, it looks like it's traveling towards the east. Okay, so it looks like it's traveling towards the east. As a result of that, this subsatellite point is actually moving further and further into this area of daylight. And if you were to go back a few hours, the subsatellite point would have been located here over the dark area. So this is actually right after sunrise. Basically, what's just happened is, as the Earth is rotated, this subsatellite point has traveled, so now it's dark, 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 sunrise, 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 and now it's mid-morning. With that said, where's the sun located? Well, I actually have an image to demonstrate that. So if you take a look, it really looks like, for the most part, the lower right portion of this globe seems to be getting the most sunlight. And this is actually very common during our winter months up here. Down here is the southern hemisphere, up here is the northern hemisphere. And basically what's happening is during this time of year, the sun is located further in the southern hemisphere. It's further over the southern hemisphere. And so sunlight is essentially coming in. If you were to use a cardinal direction, you would say something like, okay, in this situation, the sun is coming from the southeast. So in this case, sunlight's coming over from the southeast. One of the other concepts I want to talk about right here is there is actually a dividing line between the sunlit portion of the globe and the less sunlit portion of the globe, or the not sunlit portion, the dark portion of the globe. And I actually drew this here. It's a red line, and there's actually a key name for it. And this key name is called the Terminator Line. Or if you're like me and you love the Terminator, you love Arnold Schwarzenegger, it is called the Terminator Line. And basically what it is it's the line dividing the sunlit portion of the globe from the dark portion of the globe. And this actually represents where sunlight is being divided from one location to another. And right now, as the Earth is rotating, locations are moving from here over this way. They're following along with my laser pointer. They're actually moving to the east. So this is actually a sunrise Terminator line. As the Earth continues to rotate, this is where sunrise is happening. Here's another image of the Terminator Line using my Arnold Schwarzenegger impersonation. And this time, if you notice, the sunlight is actually coming from the west. And this is actually very common at sunset. In this case, the sun is setting in the west. If you ever remember, the sun rises in the east and sets in the west. And so what's happening is locations here in the west, and again, I'll use my sub-satellite point. Let's put it right over Los Angeles. As the Earth continues to rotate to the east, Los Angeles is going to get closer and closer and closer to the Terminator Line. And then once it hits the Terminator Line, that's when sunset occurs. And that's when it passes over from the sunlit portion of the globe to the dark portion of the globe. So this is a sunset Terminator Line. In this case, the bright part's on the west, the dark part's on the east. The last thing I'm going to talk about is there's this slightly confusing image at the very end of this lab that compares sunlight to darkness. And here's what's actually going on here. So this actually divides the sunlit portion, so over here and over here, to the twilight and dark portion of the globe. And there's a few things I want to mention. And the questions that are asked here are slightly deceivingly difficult. And so I want to give a few hints. The first thing is, what time of the year is this? Well, in order to determine what time of the year this is, you need to look at the sun's exact position. And specifically, if you want to determine that, you actually need to look at where the center of this sun drawing is. And right now, the center of this sun drawing is a few degrees north of the equator. So at this time, the sun is still north of the equator. This is common during the spring and summer months, and in this case, this would actually be pretty close to the equinox. That's when the sun is directly over the equator, but right now it's slightly over the equator. What actually happens is when the sun is either over the equator in the northern hemisphere or under the equator in the southern hemisphere. Sorry, using Eurocentric terms there. Anybody watching this from Australia, I apologize. But anyway, when the sun is north of the equator, okay, better, more correct term, when the sun is north of the equator, the northern hemisphere gets more sunlight and has longer days. And you can actually identify that through the width of this darkness location, or this twilight and nighttime location. It's actually a little more narrow than down here in the southern hemisphere. And the other interesting thing is, at this time, the entire North Pole is in the sunlit area. Meanwhile, the entire South Pole is actually in the twilight, and then in some portions slightly darker than twilight area. This is going to become more important in the next activity. But just to review this real quick, right now, at least in this image, the sun is slightly north of the equator, and looking at the thickness of this individual or this dark area, it is slightly thicker slightly thinner, slightly more narrow in the northern hemisphere than it is in the southern hemisphere. And as a result, the northern hemisphere is getting a little more light than the southern hemisphere is. And if you actually wanted to, I could actually post a link in the comments that actually shows a little bit more about where you can actually get like the current version of this. So that's it for right now. The next lab is going to deal a little bit more with the seasonal variation of this. And so I'll see you then.